dimeric pairs. More examples. Here again is given structural formula of ethanol. Ethanol, in this example, makes 2 hydrogen bonds with 2 molecules of water. In these hydrogen bonds, this alcohol, ethanol, behaves as hydrogen bond donor or hydrogen bond acceptor. In your opinion, what is your opinion? It behaves as both hydrogen bond donor, it donates an atom for formation of a hydrogen bond, and hydrogen bond acceptor at this oxygen atom. What is the name of this organic compound? You see? Nobody knows. Ether, dimethyl ether. Hydrogen bond between dimethyl ether and water molecule. In this hydrogen bonding, it behaves as hydrogen bond donor or hydrogen bond acceptor. No, acceptor. Because it donates lone electron pair at oxygen atom. Hydrogen bond donor is water in this bond. What's the name of this compound? Or this? It is the same. Aminobenzene. The other name is aniline. So aniline molecules can form hydrogen bonds through hydrogen atoms, nitrogen atoms. So we can say that aniline molecule can be both hydrogen bond donor, hydrogen bond acceptor. What is the name of this compound? This one. CH3COOH. I showed this compound 50 times, especially when we talked about buffer solutions. Acetic acid, ethanoic acid, of course. And here are shown hydrogen bonds of carboxyl this acid with water molecules. Next example, ammonia molecule makes hydrogen bonds with water molecules. Ammonia again, hydrogen bond with water molecule. Which is the difference between these two hydrogen bonds? There is a difference. And what is this difference? Because both water molecule and ammonia molecule can be hydrogen bond donors and hydrogen bond acceptors. So, in this example, ammonia is hydrogen bond donor. Water is hydrogen bond acceptor. If we write hydrogen bonding in this way, here water is hydrogen bond donor and ammonia is hydrogen bond acceptor. Both are correct. If you will be asked to show hydrogen bond between ammonia and water molecule, you can show both of these and it will be correct. Low molecular carboxylic acids such as methanoic, ethanoic acid, even in gaseous state, can form two hydrogen bonds between two molecules which are named dimers. And here the dimer structure is shown between two carboxylic acids. Same dimeric structure between molecules of ethanoic acid, of acetic acid. Sometimes in water solution, carboxylic acids can make each of these molecules two hydrogen bonds with two water molecules. Each carboxylic acid can make up to 5 hydrogen bonds. 2 bonds at these oxygen atoms, 2 more at this oxygen atom, and 1 using hydrogen atom of the carboxyl group. Second type of hydrogen bonding is named intramolecular hydrogen bonding. The name shows that inside the molecule, hydrogen bond will be formed. Usually, such hydrogen bonds arise when we have ortho derivatives of benzene. For example, salicylic acid. The other name of salicylic acid is ortho-hydroxybenzoic acid. Salicylaldehyde, we can name it also ortho-hydroxybenzaldehyde or orthonitrophenol. What is what is the requirement of such intramolecular hydrogen? The groups participating in this hydrogen bonding be close others, so such bond to be realized. And you can see that the hydroxyl group and are very close to each other. In the second example, again, hydroxylaldehyde group next to each other, or hydroxyl and nitro group are very close at ortho position. Another example of such intermolecular hydrogen bonding, and I could say this is a very good example of equilibrium tautomerism, is the molecule of acetoacetic ester. Maybe it looks complex, it looks complicated, but in organic chemistry, we have topic aldehyde and ketocarboxylic acids. So for the final exam, you have to know the formula, the structure of acetic acid. Aceto, you can see part of acetic acid, aceto, and second part of acetic acid, acetic acid. And this is ester, ethyl ester of acetoacetic acid. In this structure, we can see carbonyl group, CO group, carbon atom having 2 hydrogen atoms, and again CO group, this is CO group. There is again carbonyl group. So with these hydrogen atoms and this carbon atom are between 2 carbonyl groups, between 2 keto groups. So it is easy, hydrogen atoms move to another atom group. And here we have example of tautomerism, tautomeric isomerism. Tautomerism means when we have change in the position of double bond and in the position of hydrogen atoms. So, realizing isomer of this acetoacetic ester, you can see the position of double bond is changed here. The position of this hydrogen atom is also changed. It goes to carbonyl oxygen and forms OH group. In case we have carbon atom involved in double bond and hydroxyl group, we say this is a null structure. NO. N shows that we have double bond, and O we have when we have alcohols. So usually such structures are not stable. I'll repeat this. I'll show again that enols, enolic structures are not stable. But due to formation of hydrogen bond, intramolecular hydrogen bond in this enolic structure, it becomes stable. And here is shown that enolic structure exists in equilibrium with ketoform about 10%. The reason of this is formation of hydrogen bond between this oxygen, carbonyl oxygen, and hydrogen of the hydroxyl, enolic hydroxyl group. Another reason, which I'll mention later, is existence of conjugation between these double bonds. So there is double, single, double bond, and in such case we say there is possible conjugation between these bonds. What happens when we have meta or para derivatives? In meta and para derivatives, functional groups are not each other, they are each other. In such cases, they can only in intermolecular hydrogen bonding, which intermolecular hydrogen bonds in para-hydroxybenzaldehyde can be shown and realized in this way between molecules. Hydrogen bonding in hydroxybenzoic acid can be shown in this way. How hydrogen bonds, inter and intramolecular influence physical properties of compounds. Here you see ortho-hydroxybenzoic acid, meta-hydroxy and para-hydroxybenzoic acid. Molecules such as salicylic or ortho-hydroxybenzoic acid having intramolecular hydrogen bonds cannot interact each other to form intermolecular hydrogen bonds. That's why they possess lower melting and lower boiling points. And here you can see melting points of salicylic acid, meta-hydroxybenzoic and para-hydroxybenzoic acid. Salicylic acid molecules involved in intermolecular hydrogen bonds can make only attractive forces which are determined as dispersion forces. So between salicylic acid molecules exist dispersion forces. But if we have para-hydroxybenzoic acid between molecules of para-hydroxybenzoic acid, intermolecular hydrogen bonds exist. That's why we can compare melting points of these two hydroxybenzoic acids. Low melting point of salicylic acid because between molecules of salicylic acid, dispersion forces exist, which are very weak, non-covalent forces. And the melting point of para-hydroxysalicylic acid is high because of intermolecular hydrogen bonds in molecules of this compound. Strength of hydrogen bond. So this type of bonding has electrostatic nature, and obviously the strength is on depends on polarity of such bonds, on polarity of covalent bonds in which hydrogen atoms are involved, and it depends on the distance between such dipoles. The short distance, the stronger will be hydrogen bond. So, bonds in which nitrogen and fluorine atoms participate. If we talk about electronegativities, the more electronegative atom is fluorine. Also, large electronegativities possess nitrogen and oxygen atoms. But if we try to show or to detect hydrogen bondings in which electronegative atoms such as chlorine, iodine, sulfur are involved, in these cases, we can regard such bonding between molecules having these atoms like dipole-dipole interactions, but not bonding. Why? First, the size of these atoms is large. And second, sometimes the electronegativities are smaller than the electronegativities of nitrogen, oxygen, or fluorine. But you can see in the last sentence here at the slide that electronegativities of nitrogen and chlorine atoms are almost the same. But chlorine atom, because of its large size, cannot participate in hydrogen bonding. Why? Because only the size of these three elements is comparable with the small size of hydrogen atom. Hydrogen bonds, strength and magnitude of hydrogen bonds depends on the strength of given hydrogen bond and depends on the number of hydrogen bonds. If we talk about the strength of the dipole between hydrogen atom and oxygen, nitrogen, or fluorine, obviously the strongest or the largest dipole will be when we have fluorine, the most electronegative atom. And let us give again the example we used last time. Hydrogen bonds between molecules of hydrogen fluoride, and molecules of water. Hydrogen bonding influences physical properties, especially boiling points of compounds. Hydrogen fluoride boils at approximately 20 degrees Celsius, while water boiling point is around 100 degrees Celsius. In fact, the hydrogen bond between hydrogen fluoride molecules is stronger, but the number of hydrogen bonds between molecules is 1/1 hydrogen fluoride molecule. Hydrogen fluoride molecule has one hydrogen atom to donate for hydrogen bonding and 3 lone electron pairs around fluorine molecule. In case of water, each water molecule can make 2 to 4 hydrogen bonds with neighboring water molecules. If we talk about ammonia, this is molecule of ammonia. We can see that ammonia has 3 hydrogen atoms that can participate in formation of hydrogen bond, and only 1 electron pair also available for hydrogen bonding. In case of water, we can say there is proper balance between hydrogen atoms available for hydrogen bonding, and also lone electron pairs, which can participate in hydrogen bonding. 2 hydrogen atoms and 2 lone electron pairs. And This is the picture formation of 4 hydrogen bonds by one water molecule with other water molecules. Hydrogen bond length is given 0.16 something, which means hydrogen bond is longer than a common covalent bond between, for example, oxygen and hydrogen, which is given to be 1.007 nanometers. To be longer means to be weaker than corresponding covalent bond. I have another option now. Okay, I'm prepared. Don't worry, I'll share in. Let me find the slide I am looking for. Okay, now I have to share the screen. Okay. The set of hydrogen bonds depends on the number of hydrogen bonds also. Let us look at melting points of these examples. What is the name of this compound? Louder, please. This one, this one. Ah, you can not see. The first one. At my screen, I see. First one. Ethanol. Let me. Now? No. Okay. I'll explain without. I'm not sure. Not able to show. Maybe I'll need to take another thing. Oh, help is coming. No problem. Виждам курсора просто. Другото всичко е наред. Но аз съм сега на споделен екран. Трябва да escape.
Не знам дали може да се види.
Сега ще курсора. Вече. Пак да го направи на голямо. So this is ethanol molecule. Ethanol molecule. Would you stop talking and take your seats, please? Some students changed their seats today. Okay. 3 hydrogen bonds. The positions for making such hydrogen bonds are shown. This compound, now you can see which compound I'm asking for. Five hydrogen bonds. Also, this compound, oxalic acid, very much correct. Ако пак, добре, с кое се състои? Аха, да, си. Oxalic acid is the simple carboxylic acid which can be regarded as organic acid, the simplest carboxylic acid. Oxalic acid, usually we write as H2C2O4, like mineral acid. Oxalic acid you use during next practical classes when you study redox processes and the same number of hydrogen bonds, but different polarity of hydrogen bonds. Also, the strength is different. Example, aminoethane. The other name of this compound is ethylamine. 3 hydrogen bonds are possible. Ethanol. Again, 3 hydrogen bonds. But if we look at the boiling points of these 2 compounds, look, aminoethane boiling point is about 17 degrees Celsius. The boiling point of ethanol is 80 degrees Celsius, higher. And this is because the strength of hydrogen bonds between these molecules is different. The stronger are hydrogen bonds between molecules of alcohol, because the electronegativity and the resulted polarity of the bonds is higher between molecules of alcohol. Let us discuss hydrogen bonds between water molecules. Here are shown water molecules in liquid water. And here, structure of hydrogen bonds between water molecules in solid state, in ice. You can see that the ice, water molecules, due to formation of hydrogen bonds, form very ordered structure, so named open structure, in which open structure, each water molecule forms 4 hydrogen bonds with neighboring water molecules. In the liquid water, this ordered open structure is destroyed, and the number of hydrogen bonds decreases. But such a structure leads to less density of ice and less dense ice can float during the winter on the surfaces of rivers, of lakes, which helps water organisms to survive the water. Hydrogen bonds are very important for physical properties of the compounds. We already have had several examples about this. Melting, boiling points, solubilities of compounds involved in hydrogen bonds are larger. Also, they are important for biological systems in which compounds make hydrogen bonds with molecules of water. You see several examples in the next slide for hydrogen bonds, which are very important for the structure of proteins, of nucleic acid, cellulose, and several examples of biological importance of hydrogen bonds. At this slide are shown hydrogen bond donor groups, hydroxyl group, amino group, and hydrogen bond acceptor groups, keto group, nitrogen atom of heterocyclic compound, oxygen atoms, again are hydrogen bond acceptors. Hydrogen bonds are very important for the secondary structure of proteins. You can see these red dotted lines in alpha helix, which show hydrogen bonds between carbonyl group and H group of so-named amide groups. What is amide group? You start amide group later. This is CONH group. And also such hydrogen bonds exist in beta sheets between amide group, this group, CONH group, properly orientated each other. Hydrogen bonds are very important for DNA double helix. We will study later the structures of pyrimidine and purine bases. In DNA helix, each pyrimidine base is bonded through hydrogen bond with purine bases. Purine bases are adenine, guanine. Pyrimidine bases, cytosine, uracil, thymine. So in DNA, thymine molecule makes two hydrogen bonds with adenine molecule. They are complementary. Cytosine makes three hydrogen bonds with guanine. And usually this double helix is shown in this way, meaning that this thymine, adenine, guanine, etc. At the end of this study of different type of bonding in biological models, using tertiary structure of protein, we can show that in proteins, all types of bonding exist. Disulfide bond is typical covalent bond, which later we will study could be intramolecular or between protein molecules. Hydrogen bond. Ionic bonding. When we study amino acids and peptides, we will know that side chains of some amino acid at pH 7.4 are charged. So, probably you know that, for example, two of standard amino acids are negatively charged, and 3 are positively charged. So, between charged side chains of amino acid can be found ionic bonding. This is side chain lysine, and this is side chain of aspartic acid, positively, negatively charged. Also, van der Waals interactions exist between non-polar side chains of proteins. And usually these non-polar side chains are aligned in a way in which they are they ensure water avoidance, and they act as typical van der Waals interactions of forces. Same. I simply copied some pictures showing that hydrogen bonds exist in protein structure, disulfide bonds, ionic bonds, van der Waals between a non-polar side chain, CH3, this is alanine amino acid, and these are amino acids such as valine, leucine. These interactions are named van der Waals or hydrophobic interactions. In this way, we completed this topics from 1 to 3 regarding bonding in compounds. So I have a question. I'm not sure whether I will be able to see the answers of students which are I'll try. For my regret, I won't be able, but I'll use the time to make an announcement about attendance of practical classes in chemistry. I hope all the students at home and also in the virtual classroom can hear this. All practical chemistry classes should be attended in person. Please, all the students which already arrived, attend practical classes in chemistry in person. Я с другой стороны, да. Most of the students already arrived. We have information that no more than 50 students are missing. So please attend regularly practical classes in person. There are only 40 to 50 students who still have visa problems. But they will arrive soon and they will join us. I see that in virtual classroom there are about 70 students. It shouldn't be. Please attend in-person lectures and practical classes. All the students already arrived in 11. Next week, we will have very important practical classes. You need to work, everyone. You have to work with test tubes, burettes, pipettes, etc. So be a person. Now we can continue. I don't know in which way I. Interaction already studied many types of bond. Amide bond, I gave you example. It is NH-CO bond, which is covalent bond, kind of covalent bond. What is the correct letter? D, dispersion forces, the weakest forces. Please find the proper example of dipole-induced dipole interaction. Which letter? E. Oxygen and water is correct answer. And this example is given in this table you have seen last time about different types of non-covalent bonding. Which of these compounds cannot form hydrogen bond? These compounds are given by their names, but all of these compounds contain hydrogen. Which one cannot be involved in hydrogen bonding? D. D or C? D. Ethane. Ethane. D is correct answer again. And here you have to read and to find a wrong statement. Again, D. It is not possible partially positive hydrogen to attract electron pair from a partially positive atom. No sense. Which compound? Name. Salicylic acid. Correct. Thank you very much. I gave you this example several times. This compound able to form intramolecular hydrogen bonds. I think this is the last question. You have to compare boiling points of these two compounds, both having the same molecular formula, different structure. These two compounds are isomers. What kind of isomers are these two compounds? Functional isomers. Thank you. Why you changed your seat? You are sitting 2 rows. Okay. Functional isomerism because this compound is ether and this is alcohol. But which of these has higher boiling point? Yeah? This one. What is the name? Thank you. Correct. Especially propane 1 or 1 propanol because the hydroxyl group is directly bonded to the first carbon atom. Here, alcohol makes hydrogen bonds between molecules. Between molecules of ether, it is not possible to make hydrogen bonds. That's why ether's boiling point is very low, and alcohols, for example, if we take this example with ethanol, boiling point is around 80 degrees Celsius. And this is the end of this topic. Now, I'll try to start, and I will start, not only try, another topic. Oh. Topic number 4, coordination compounds. Again, my cursor, please don't see. Okay, coordination compounds are specific type of compounds which are present in biological structures. So we have to study these compounds. Usually, coordination compounds, we can regard their bond between simple compounds. For example, salts interact silver cyanide and potassium cyanide to form complex or coordination compound. How can we recognize, looking at the structure, that these are coordination compounds? Usually, coordination compounds, some groups square brackets. And what is typical is that in water solution, coordination compounds produce stable complex ions. You can see if these two compounds, silver chloride and 2 molecules of ammonia, interact, a coordination compound, this is formed. But if this coordination compound after that in water, it will release complex ion. This ion, which is shown in brackets, complex ion. The charge of complex ions can be positive or sometimes negative, can be 1, 2, 3, 4. You can see these examples. So we can say that coordination compound meaning ions. But sometimes we'll see with the next examples, coordination compound can contain simply complex, which is neutral, can be a charge. Let us involve some terms typical for this compound. Central metal ion or central metal atom. In each coordination compound, there's central metal ion in all these examples. Sometimes such complex can contain central metal atom, not ion. Usually these are elements of D elements, sometimes E elements, aluminium, non-metals such as nitrogen, chlorine, sulfur. As elements, calcium, magnesium also can make coordination compounds. I already explained typical coordination compound contains central metal ion. But times we have these next examples of nickel tetracarbonyl, pentacarbonyl, benzene, chromium. All these coordination compounds contain central metal atom, which means that this central species in this complex is neutral. It has no charge. While in most other examples, central metal ion bears charge. Around central metal ion or central atom placed ligands or ligands, I'm not sure about pronunciation. Ligands regarded as Lewis bases. What was definition of Lewis base? Donor of electron pair. Central metal ion or atom usually contains empty atomic orbitals, so it behaves as Lewis acid. So the bond between metal and ligands is a coordinative bond, type of covalent bond. When we talk about ligands, in the molecule of ligand usually is atom directly bonded to the central metal ion or central metal atom. And such atom is named donor atom because this atom donates electron pair to the central metal ion. And in this example, complex of copper ion, central metal ion, with ammonia ligands, donor atoms are nitrogen atoms of ammonia molecule. Coordinate covalent bond in these coordination compounds. Usually, one of the species participating in such type of bonding donates electron pair, and the other behaves as acceptor of this electron pair. And as a result, they give bond. We already discussed this type of bonding is realized. For example, cobalt 3+ ion, metal ion, interacts with 6 ammonia molecules. Cobalt 3+ ion possesses empty atomic orbitals, which can be occupied by 6 lone electron pairs of nitrogen atoms of ammonia molecule. And in this way, the complex between cobalt and 6 ammonia molecules is formed. In fact, we can say this is acid-base interaction in the framework of Lewis theory. We already studied this theory. We already studied this formation of so-named adduct in the Lewis theory about acids and bases. can regard this species ammonia cation, hydronium cation, or boron trichloride ammonia as coordination compounds. And here we need to mention again that this coordinate covalent bond formation is different than the common covalent bond. But only mode of formation is different. After formation, all these bonds between nitrogen and hydrogen atoms are indistinguishable, or between oxygen and hydrogen atoms. Another term, coordination number of central metal species. Usually, coordination number is equal to the donor atoms of ligand bonded to central metal ion. Example, coordination number of silver in the complex with ammonium molecule is 2. Coordination number of copper in this complex is 4. Or coordination number of iron in the complex with cyanate ions is 6. What is coordination number of cobalt when we have not the same but different ligands? 5 ammonia molecule and 1 chloride anion. 6. Sum of donor atoms. 1 chlorine atoms from the chloride anion and 5 nitrogen donor atoms of the ammonia molecules. Usually, coordination number, and in most cases, coordination numbers of different metals are 6 or 4. Sometimes coordination numbers of 3, 5, 7, 8 can be found. We cannot predict the coordination number because coordination number of central metal ions depends on many things. Nature concentration of central metal ion and ligands, temperature, concentration, nature of solvent, etc. Another term we have to introduce today, inner sphere, also named coordination sphere or complex ion. In brief, inner sphere is everything included in these square brackets. So, inner sphere. Everything in this included in these square brackets, which means inner sphere consists of central metal ion plus ligands. Counter ions, another term. Usually, coordination compounds are neutral compounds. They contain complex ion and counter ions. Counter ions are ions outside inner sphere. So, if we take this compound, cobalt central metal ion forms complex ion with 5 ammonia molecules and 1 chloride ion. So, central metal ion ligands. But outside this inner sphere, ionizable sphere, non-ionizable. Inner cannot be ionized. Outside this are chloride ions, two chloride ions, which are outer sphere, are also named counter ions. Why counter ions? Because the charge of complex ion is 2 plus. Plus to 0. So coordination compound is neutral compound. What happens when we dissolve in this compound in water? It dissociates complex ion and counter ions, two chloride ions. And I already mentioned that some compounds haven't outer sphere, like coordination compound of cobalt with 3 calculate cobalt oxidation number is 3 plus, and there are 3 neutral ammonia molecules and 3 chloride ions. The charge of the whole compound is 0. So this compound has no outer. Depending on the number of donor atoms, we can classify ligands as monodentate or polydentate. The name shows that they have only one donor. Examples of such monodentate ligands if coordination compound complex in which all the ligands are monodentate, this means coordination number of central metal ion will be equal to the number of monodentate ligands. And again, examples of such ligands. Chloride, bromide, iodide, anion. The formula and Lewis structure showing lone electron pairs, water, ammonia, hydroxide anion, carbon oxide, anion, cyanate anion also. Bidentate ligands have 2 donor atoms. Examples. Ethylene diamine. Remember this structure. We'll give in the next slides or tomorrow more examples. It is organic compound. Ethylene in the middle, diamine at 2 ends. This structure sometimes is written in this way, or even in formulas. There are 2 donor atoms, 2 oxygen atoms available for and heterocyclic compounds, dipyridyl 1,10 phenanthroline. There are also ligands containing more than 2 donor atoms, polydentate ligands, such as triphosphate anion, which participates in structure adenosine triphosphate. Also, polydentate ligand ethylene diaminotetracetic acid you use in practical exercises. So try to learn this structure. I just found how to remember ethylene in the amino and after tetraacetic acid. It is creation of this. And regarding ligands, here we can introduce also heteroleptic complexes. Homoleptic complexes, in these complexes, on one kind of ligands are present, such as complex. In heteroleptic complexes, ligands are different. Like in this example, ligands for ammonium molecule and 2 chloride ions. Another term which you have to be able to determine: oxidation number of central metal atom. Let us take this example: platinum, 4 chloride ions. The charge of this ion is 2-. We can calculate, if we put platinum oxidation number to be X, X plus 4 minuses, X minus 4 should be equal to -2. And in this way, we calculate the oxidation number of platinum to be +2. It is easier to calculate the oxidation number in the complex of copper with 4 ammonia molecules. Because ammonia molecules are neutral, then they don't bear charge. In that case, the oxidation number of copper is the same as the charge of the complex. And everything regarding terminology used here is explained in this example. So we have complex ion. In this example are shown as of the outer sphere. Central metal ion is cobalt ion. Ligands, 2 ammonia molecules and 4 chloride ions. What is the charge of complex ion? For my regret, I calculated and showed. Charge is 2-, because outside we have 2 potassium plus, 2+. 2 ammonia neutral molecules and 4 negative chlorine ions. The oxidation number of cobalt is 2+. In this way, you can calculate the charge of the ion, the coordination number, the oxidation number of central metal ion. What is coordination number now? Of cobalt in this example? No, no 4. 6 is better. Okay, in this way, we'll stop for today. We'll continue tomorrow. For my regret, we still have lectures in this hall. I